Guys, hope all of us are doing fine. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In my discussion today, I'm going to look at arithmetic operations of or with complex numbers, and this is going to be compounding on the previous discussion whereby we looked at the concept of complex numbers and how we can represent them in terms of graphs and phasor as over Z. Now, in this particular case, I'm going to have an additional, of course, idea or an additional concept which is going to be including another additional phasor, and the two are going to be assisting us in trying to, of course, perform some of the arithmetic operations which we're going to see being done on complex numbers. Now, in this case, we're going to consider a phasor which we had just used in our previous discussions, which we're going to see being given in terms of this specific representation of a Z. And this is going to be represented generally given this specific aspect for the real part and the complex, or the imaginary part and the complex, the real part and the imaginary part given as such. And if we consider having another phasor which can be given in terms of a P, so P can be represented using the real part given as P plus the other part which we're going to consider. Or if we have another phasor which can be given in terms of a W, so this is going to be given in terms of the real part and another, of course, imaginary part which can be given in terms of IQ. So we're going to treat the two, of course, complex numbers and try to see how we can perform various operations on them. And then this is going to be constituting the basic operation of addition, subtraction, and perhaps division or multiplication, which we are going to consider in this case. So for the first case, if we consider the addition of the two, of course, complex numbers, this can be given in terms of a representation of the sum of the real parts, which are x plus p, and then we're going to have that one, of course, together with a sum of the complex or the imaginary parts given in terms of y plus q given as such. So this is going to be the basic steps which we are going to take in case we have two complex numbers which are going to be added. And as we can see, there is a specific trend whereby we're going to first start the operation by addition of what we refer to as real parts, and then we're going to have the imaginary parts which are going to be forming another set of sum given as such. So we are going also to consider a case whereby we're going to have this subtraction of this particular, of course, set of complex numbers. And in this case, we're going to perform a similar operation, only that this is going to be a subtraction. So basically, the real parts are going to be added, and then we shall have, of course, the subtraction of the imaginary parts given using that specific representation. And if you consider that part, which is going to constitute perhaps a multiplication of these two complex numbers. So in this case, we're going to have these ones, of course, given in terms of their various representation for the x, I, y given as such. And we're going to have this one as a factor multiplied with a p plus I, q given as such. So we can perform this evaluation by having basically doing the normal operation as we do for, of course, these specific other different factors, especially if we consider this one to be linear factors, and therefore we can just perform this normal operation over x times p, and then we're going to have xi q, and then we're going to have plus I y p plus I y I q. Now, in this case, I'd like us to consider this specific aspect, whereby we're going to have this specific equation represented in terms of this particular aspect of xp, which is going to be consisting of these real parts being multiplied. Now, the rest of the factors for the next three, of course, we're going to see that they're going to constitute of this specific aspect of I. And in this case, for the last part, or this imaginary unit, which can be given in terms of this representation. And of course, we're going to consider this. And for the last case, we're going to see that it's going to be consisting of this two specific components for imaginary, of course, units. Now, if we consider this case for an imaginary unit, which is going to be multiplied by another imaginary unit, so this is going to be having an implication of multiplying two square factors of those specific representation. and this is going to be giving us a value of a -1. So this implies that if we have a square of that imaginary unit, then therefore it's going to be giving us a result of course, a -1 given as such. So then, therefore, if we have this specific representation, we can just rearrange this one and have a imaginary unit together with a xq, and this of course is going to be yp, which has been separated. So we're going to have a common factor for the imaginary unit given as such for the product, or the sum of xq plus yp given as such. Now for the last part, we consider this specific notes which I've just given on the top right part of the board. Then therefore we're going to have these two imaginary units giving us a -1. So this one will have an implication that the last factor which is going to be considered, of course, is going to be having a product of y p given as such, and this is going to be representing our product for the two complex numbers which have been given as such. So the last case, we're going to consider what we refer to as a multiplication, and this is going to be constituting a multiplication of these two specific complex numbers which we have given for z and w. And this can be given in terms of this specific representation, whereby we're going to have particularly the z divided by w. So in this case, we can represent this one still using this specific notation, and thereby this is going to imply that we can have this given in terms of x plus I, or the imaginary part all over imaginary parts times y plus p plus the product of the imaginary parts and q given as such. Now, in our previous statements, we have talked about the concept of, in our previous discussion, I talked about the concept of a complex conjugate. Now, for us to evaluate this one, we're going to involve the idea of a complex conjugate, and therefore this is going to be represented using this specific aspect of at the face of z or at the face of w, and we're going to have a complex conjugate of the, this is going to be the numerator, the denominator. So we're going to have a complex conjugate of the denominator given in terms of w bar all over w bar given as such, and this is going to be multiplied by both to both the numerator and the denominator given as such. So this one is going to imply that we're going to have the, a division of these specific two complex numbers given as such, and we're going to have p plus I q. Now the complex conjugate for the denominator is going to be given in terms of p minus I r minus the complex imaginary unit times q, and then we're going to have it still being represented on the numerator side given as such. So this one has an implication that suppose we have two linear factors which are going to be given as such, we can consider this one to be a difference of two squares in terms of their specific product, and therefore this is going to be represented in terms of our denominator given in terms of the square over p plus the square of this other section of what we refer to as a q, and this is going to be given as such. So remember from our previous discussion on this specific notation we had given, in this case they are going to be a square of these two, but it's going to be a negative sign which is going to be accompanied due to this specific case. So we shall have a negative times a negative, which is going to be giving us a positive, and therefore we shall have the difference of these two squares in quotes being given in terms of a positive, so which is going to be basically forming a sum of the squares due to this inclusion of this aspect of the complex unit being given in terms of a square. So for the numerator, we are going to have a specific representation which is going to be having the product of these two. As we said, this can be evaluated using, so perhaps I'm just going to be giving it as such. So you can do an evaluation for the two and try to see what is going to be achieved from that. But from my end, I'm finding a negative the imaginary unit xq plus I, or the imaginary units yp, and then we're going to have the plus the last part, which is going to be yq given as such. So this is going to be forming this specific product which we're going to have xp minus imaginary units xq plus imaginary units yp plus yq, and this is going to be all over p plus the square of those two specific factors which we have given as such. So this is going to be forming what we refer to as the division of the two, and this is one of the ways in which we are going to find what we refer to as an operation, or which is going to be dealing with the division of two complex numbers. Now, for that case, we can consider a general example, which is going to be assisting us trying to represent this specific operation of a complex number using the strategy which we have just employed on the board. And therefore, I'm going to have this specific representation, whereby we're going to be required to obtain. So if we are required to obtain a complex number z, if we're required to obtain a complex number z, or the face of z satisfying this specific, of course, a combination, whereby we're going to have the face of z minus 1 all over 2 minus the imaginary unit is equivalent to 2 all over 1 plus the imaginary unit given as such. So if we are required to obtain the complex, of course, number which is going to satisfy this specific equation, then we're going to, of course, perform an operation which is going to be assisting us represent basically this phasor of z in terms of a complex number. So we are going to do a rearrangement of basically a cross multiplication of this specific, of course, different parts of this specific equation, whereby we're going to have the face of z minus 1 represented as 2 times 2 minus the imaginary unit, and this is going to be divided by 1 plus the imaginary unit given as such. So we can still simplify this and have it in terms of 4 minus 2 the imaginary unit all over 1 plus the imaginary unit given as such. And this can as well be further evaluated from the previous discussion, whereby I said about the complex conjugate of this specific representation. So in this case, we are going to have this phasor minus 1 represented in terms of 4 minus 2 the imaginary unit plus 1 the imaginary unit. So we're going to take a complex conjugate of the denominator, which is going to be given in terms of 1 minus the imaginary unit all over 1 minus the imaginary units, whereby these are going to be forming a complex conjugate of particularly the denominator which has been given as such. And this can be evaluated to give what we refer to as this specific equation, which is going to be simplified. So in this case, we're going to be, just as we do the normal operation for multiplication of such a kind of factors, we're going to take 4 times 1. And this is going to be giving us an equation of the form of 2 minus, of course, we're going to have this one as an imaginary unit over 2. And this can be further simplified. So this is going to be giving us the phasor of z given as such. And this basically can be evaluated. So this is going to be giving us, so let's just solve it without just using that shortcut. So we shall have that one given in terms of 4 minus for the imaginary unit, which is going to be 4 times 4. 1 is equivalent to 4. 4 times negative the imaginary units 4, and the negative minus the 4 negative out of 4 the imaginary units given as such. So this is going to be minus 2 the imaginary units times 1. So this is going to be giving us 2 the imaginary units as given as such, and this is going to be 2 times the imaginary units times the imaginary units. And this basically is going to be giving us a value of 2, considering the square of those imaginary units given in terms of negative 1. So in a sense, we are going to have the lower section represented by, of course, 1 plus 1. So considering this negative sign, we are going to have this specific case, and then a negative minus 1 is going to be equivalent to a positive 1. So this is going to reduce to a form of basically what we're going to have as 2 minus the imaginary unit times 6 all over 2. And this, as we can see, can be arranged in terms of 2 into 1 minus imaginary unit 3 all over 2. So we're going to have this phasor minus 1 equivalent to 1 minus or the imaginary units times 3 given as such. And this can be rearranged further to obtain the value of the face of z, which is going to be, of course, a complex number that we require in terms of so this is going to be 1 plus 1 minus the imaginary unit times 3. This is going to be 2 and then minus the imaginary units times 3 given as such. So this basically is going to be representing a complex number that's going to satisfy this specific equation by representing it in terms of a phase of z. And this is going to be forming our last part of this particular evaluation for various range of operations of complex numbers. Now we're going to do various other examples in our subsequent videos, but kindly check our description boxes for a link which I'm going to put there for topics which are going to be under a similar discussion. So that is it for now, guys. By God bless. We'll catch us in our next video.